of my silver nitrate, and I convert that into my limiting reactant. My limiting reactant was the cobalt 2 chloride. So moles of cobalt 2 chloride for every mole of silver nitrate. There were 2 moles. Look back at your balanced reaction to every 1 mole, I believe. I'll just double check. Make sure I don't do the answer key wrong. But I believe up at the top here that we had 2 to 1. Yes, we have 2 moles to 1 mole. So as I scroll back down, I say to myself, okay, I have 0.464 times 1 divided by 2. I have 0.232 moles of cobalt 2 chloride that I used. This is how much I needed or how much I used. Alright, how much was I given? I was given, if you look back at the top, I was given 1.01 moles of cobalt 2 chloride at the beginning. You take the given, you subtract the used, and you have the remaining. The used was 0.23, that's a 3, that's a 2, 0.232 moles of cobalt 2 chloride. And when you take that difference, 1.01 minus 0.232, what you get is 0.01 minus 0.232, you get 0.778. You get 0.778 moles of cobalt 2 chloride remaining. That's how much you have left over. That's how much remains, okay? Or you could say in excess. Alright? In excess. So we could do that. We could just scroll over here and say this much in excess. Alright. If you're actually at this 0.011 moles of the precipitate, the silver chloride, what is the percent error of your reaction? What is the percent yield? So in this case, we need to look back at our theoretical yield, which was 0.464 moles of silver chloride. So we were supposed to get 0.464 moles of silver chloride, and when we did the reaction, we only got 0.0111. So our theoretical yield, there we go, let's try that again. Our theoretical yield equals 0.464 moles of the silver chloride, but our actual yield is this. Okay? The actual yield is that much. So now what we need to do is we need to take we're going to find the percent yield. That's very easy, and the percent error. The yield is just your percent yield is your actual yield over your theoretical yield times 100. So that's pretty easy. So I just take my actual yield, this was 0.011 moles of silver chloride, and I divide it by my theoretical yield, which was 0.464 moles of silver chloride. Multiply these by 100, and it will equal my percent yield. So what does this equal? Well, let's check it out. It's a very, very small yield, 0.0111 divided by 0.464, and then times 100, I get 2.39% yield. So I only made 2.39% of what I actually thought I was going to make. That is my percent yield. Now let's find the percent error. Let's move it over here a little bit so we can get some more room. The percent error is a little bit harder. The percent error equals your absolute value difference of the actual yield minus the theoretical yield divided by the theoretical yield times 100. Okay, we're going to extend the page down a little bit. We're going to do our work right here. So here we go. Let's do it in red. The percent error equals then the actual yield, which is 0.0111. Let's put some units. That's what we should be doing. I should have put units for the other one. My apologies. Silver chloride minus the theoretical yield, which was 0.464 moles of silver chloride. The absolute value difference of that divided by the theoretical yield, which is 0.464 moles of silver chloride. We multiply that times 100, And what we get is, let's try that. Well, I'm just going to do 0.464 minus 0.0111. Same thing as taking the absolute value difference. Divided by 0.464. And I get, I have to multiply it by 100 times 100. I get a 97.6% error. And you notice these two numbers add up to 100. I get a 96.6% error. No, let me try that again. I get a 97.6% error. Actually, so these aren't quite adding up to exactly to 100 because it's some rounding. But that's okay. This is my percent error and this is my percent yield. All right, one last page. Here we go. Number 6a and number 6b. Given that 2.34 times 10 to the negative second grams of hexane. Hexane is C6H14. Calculate the moles of oxygen needed to completely react. So first thing, we have a combustion reaction. We're going to form water and carbon dioxide when we burn this hexane in oxygen. So oxygen gas is diatomic. We add that to hexane, C6H14. This would be a liquid, yeah, at room temperature, yes, absolutely. And then this is going to form carbon dioxide gas, and it's going to form water vapor. So I'm going to put water vapor gas. I'm going to balance this reaction. What I find is I have 6 carbons. I have 14 hydrogens. I have now 7 oxygens plus 12 oxygens, so 19 oxygens. So 19 divided by 2 is 9.5. So I put a 9.5 here. Now I have to balance this out. So when I balance this out, give me 1 second. I'm just going to 0.5, I have to get rid of the decimal. So what I do is, let me just do that in a different color. I'm going to cross out all of these exponents, all these coefficients. There's one here, it's a 1. I'm going to cross that out. I'm going to multiply everything times 2. So 9.5 times 2 is 19. 1 times 2 is 2. 6 times 2 is 12. And 7 times 2 is 14. And you can go ahead and you can highlight all of those if you want. Make sure that you know that these are the actual coefficients for your balanced reaction. All right. Now that I have my balanced reaction, I'm going to say that I have 2.34 times 10 to the negative 2, there's a negative sign there, grams of hexane. So really I have 0.0234 grams of this. Super, super small amount, right? Calculate the moles of the oxygen needed to completely react. First thing we got to do now is find out how many grams there are per mole of the hexane. So carbon equals 12 grams per mole. 12 times 6. That equals 72 grams. Hydrogen equals 1 gram. There are 6 of them. So I have 6 grams for, there are not 6 of them. There are 14 of them. There are 14 of the hydrogens. So I write down 14. So I have 14 hydrogens. So I have 14 grams of hydrogen. So I have 76, I have 86 grams per mole of hexane, C6H14. There we go. Now I'm going to take these number of grams. I have 0.0234 grams of C6H14. I'm having a tough time writing 14s. H14, and I multiply it times 1 mole of C6H14, and that's still pretty bad, 14. 1 mole of C6H14, and I divide that by my molar mass, which is 86 grams. When I do that, I will get 0.0234 divided by 86, and I will get 2.72 times 10 to the negative 4th moles of C6H14. That's how many moles of hexane I have. Alright, I can put that up here if I want. I've run out of room actually, so I'm just going to leave it down there. I want to figure out though how many moles of oxygen I'm going to need. So I need 19 oxygens for every 2 moles of the C6H14. So what I'm going to do is I'm going to just move over here. I'm going to rewrite it right here in a different color. I'm going to put it in green. 2.72 times 10 to the negative 4th moles of C6H14. Again, having trouble with the 14s. times 19 moles of oxygen. 19 moles of oxygen divided by 2 moles of C6H14 divided by 2 moles of C6H14 gives us, let's try it, 2.72 times 10 raised to the -4th, and then I multiply it times 19, and I divide it by 2. What I get is 2.58 times 10 to the -3. I need 2.58 times 10. Let's move that over. No, that's not going to work. Yeah, going to have to erase that. Let's try that again. 2.58 times 10 to the -3. So let's make that in blue so you can actually see what I'm saying. It's right here. 2.58 times 10 to the -3 moles of oxygen. So I had to just, make my answer key a little bit out of the way there. But you get the point. Alright. Now, if I'm given that 1 mole of gas at STP has a volume of 22.4 liters, how many liters of CO2 will you produce from the reaction above? Well, we take one of the reactants, either this one or this one. Doesn't matter which one. This is not a limiting or excess reactant problem. I calculated the exact amount of oxygen that I need to react with the amount of hexane that I need. So take either one of the moles, this amount of moles or this amount of moles of my reactants. I convert it into moles of my CO2 product. So it's 12 to 2 or 12 to 19. I'm just going to go 12 to 2 and use my moles of my hexane. So I have 0. Let's use a different color. So I have 0.02, nope, sorry. Let's try that again. I have 2.72 times 10 to the -4th. Let's cross that out. I have 2.72 times 10 to the -4th moles of C6H14. And what I do here is I say, well, if I had 12 moles of CO2, if I had 12 moles of CO2 for every 2 moles of C6H14, for every 2 moles of C6H14, then what I'll get is, let's try that out, 2.72 times 10 raised to the -4th. And I multiply that times 12, and I divide it by 2. I will get 1.63 times 10 to the -3 moles of CO2. So now it's telling us, it's saying 1 mole of the gas at standard temperature and pressure has a volume of 22.4 liters. So make a ratio of that. 1.0 moles of gas at STP has a volume of 22.4 liters. Is how many liters will this amount of moles of CO2 take up? How much space will it take up? So let's do that in let's do it in red. Here we go. That's a P. Here we go. We have 1.63 times 10 to the -3 moles of CO2. And I multiply that times this ratio. I put moles in the bottom now. 1.0 moles of any gas at STP. Make sure you do it at STP, otherwise this does not hold true for all temperatures. It has to be the same standard temperature and pressure. 0 degrees Celsius, 1 atmosphere pressure. I will get 22.4 liters. And when I do that math, I'm going to scroll down and put my answer down here again because I'm running out of room. I will get 0.0366 liters of CO2. I can convert that, I'm going to convert that into milliliters. No, it says how many liters, so I'm not going to convert that. I'm actually going to leave it just how it is, and this video is done. I'm just going to box my answer. Son of a gun. There we go. Got it. Boom. All right, guys, study this stuff, and good luck. And come and see me tomorrow if you need help. See if we got any more questions. No, that's it. Cool. Done.